In this video, we are going to be reviewing Newtonian mechanics. First, we'll look at the Newtonian mechanics of a single particle. Well, let's start with a few definitions. To define the position of a particle, we use a vector called the radius vector. So, if we have some coordinate system, and let's say we have a Cartesian coordinate system, then if we have a particle at some point, we'll just make a make a vector from the origin to the wherever the position of the particle is, and that's our radius vector. So to denote how fast the particle is moving, we use the time derivative of the radius vector, which we called the vector velocity. So vector velocity v is just the time derivative of the radius vector. We further define the linear momentum of the particle as p equals to mv, where m is the mass of the particle. Now, having defined some basic physical quantities, we can define the equation of motion governing the particle, governing the motion of the particle. And the equation of motion is actually given by Newton's second law. Newton's second law essentially says that there exist some reference frames such that uh, such that this holds this equation f equals to dp dt, and we usually write the time derivative as dot. So here we can write r dot. So this is Newton's second law, and this defines this describes the this is the equation of motion of a particle, and it only holds in certain reference frames, and those reference frames are called inertial or Galilean reference frames. You're probably more familiar with a different form of this equation, and that form of the equation of which is usually known as Newton's second law um, comes from the fact that in most systems that we look at, the mass does not change. So if the mass is constant, i.e. the m dot is zero, so the rate of change of mass is zero, then p you can put an mv over here, and f just becomes mass comes out of the derivative dv dt. And of course, what is dv dt? What is the derivative of velocity with respect to time? It's the acceleration. So you get f equals to ma. So in this way, we have defined acceleration as well, and we get the usual form of this Newton's second law. Now, with this, um, what we can further do is we can observe that if the net force, if the force on the particle is zero, if the force on the particle is zero, then p dot or dp dt is zero, right? Then dp dt is zero. What does that mean? That means that p is a constant. That momentum is a constant vector. So this is the law of conservation of linear momentum. If the force on the particle is zero, then its momentum is conserved. So this is the law of conservation of linear momentum. Okay. So this is a very brief review of linear motion for a single particle in the Newtonian formalism or the Newtonian formulation. Now we can talk about rotational motion of the particle, and to do that we have to define the moment of the momentum or the angular momentum. And the angular momentum is denoted by L, and as I said, it is the moment of the momentum of the linear momentum r cross p. Similarly, we have the moment of the force, which we call torque, and torque is denoted N, and as I said, it is the moment of the force r cross F. Now, what we can do is we can try to get an equation of motion for rotational motion for the single particle. So we can start with the equation for the torque, N equals to r cross F, and we can put in the equation of motion for linear motion here. So F becomes dp dt from Newton's second law, right? And what we're actually going to do right now is that we are going to add to this something which is zero. I mean, you can always add something which is zero, it doesn't really do anything. So we're gonna add v cross v. And why we are doing this is will become clear in the next step. But cross product of a vector with itself is obviously zero. We're just adding this here, and I'm also putting in the mass m here so I can make a momentum. And so what you see is if you have this mass over here, so let me just write it differently, mv. So this becomes momentum, this is velocity, and you see this is momentum, but this is only position. So we have a derivative of momentum here and derivative of position here. So I could write this as dr dt, right? So now you can observe that this is really the product rule. So this thing is zero, but we're just adding this so that we can take the derivative outside. So since this just becomes the product rule, we can take the time derivative outside. And what do we have? We have r cross mv is just p, as I said, r cross p. And what is r cross p? Well, we just defined it over here. It's the angular momentum. So what we have obtained is that the torque is the time derivative of the angular momentum of a single particle. Or we can just write it L dot. And what does this actually show? What we can, what this essentially gives is the equation of motion for uh, for rotational motion of a single particle. But furthermore, what we can deduce from this is that if the torque on the particle is zero, then the time derivative of the angular momentum is zero, i.e., the angular momentum is a constant vector. And this is the law of conservation of angular momentum. Conservation of angular momentum. Right? Now, let us define a new quantity that will be quite useful, and this quantity is called work. So work is really defined from some point to another, or one configuration to another configuration. Say the particle starts here and it moves to somewhere here. Let this be 2, this is position 1. And work is really defined as the line integral from point 1 to point 2 of f dot ds, where ds is really the path from 1 to 2. Now, what we can do is we can actually look at this formula two different ways. So for the first way, let us just consider the particle's mass to be constant. Since we have one particle, this is not uh, this is not a big assumption. It would be true for most cases. So let's just say for constant mass, we can write the work in this way that F is of course dp/dt, right? But because we have constant mass, P is mv, mass just comes outside, and we have dv/dt here. Okay. Now I actually want to write ds in a different way, because ds is of course the line element. So if I have ds dt and dt, I could write this as ds dt, and ds dt is of course the velocity, and I get dt here, right? So what this essentially gives me is I can rewrite this dv dt dot v as half dy dt v square. So this is very simple algebra, very simple vector algebra. You get the half outside m, and of course you get the differential, the integral of the differential just gives you the same value. You have v square, v square position 2 minus v square in position 1. So half mv square in position 2 and half mv square in position 1 will denote this quantity as t, and you should remember that this quantity is of course equals to half mv square is of course called the kinetic energy, the energy associated with the motion, right? So one way of looking at the at work was by looking at the velocity, and that actually gave us this this formula that the work done from point 1 to point 2 is really the really equal to the difference in the kinetic energy from the in the 2 points at the 2 points. Now we will look at the work done in a different way, right? So let us say let us consider forces that are conservative. For conservative forces, so what are conservative forces? Conservative forces are defined in this way, that work done is same along all paths, along all paths. So if the particle starts here and goes here, it can go straight, or it can go in a very uh, not straight way, in a slanted way. It can go like this, and the work done from point 1 and point 2 point 2 would be the same. So what this essentially means is that, say the particle starts at 1 and goes to 2, and then it's again returns to point 1. So the work done doing this way is equal to the work done this way, but it's just in the negative position. So the work done in a closed loop is obviously 0, right? So f dot ds in a closed loop has to be 0. And if you remember your vector calculus, then this means that the force is necessarily the gradient of some function of position. And we put in a negative sign by convention, and this function of position is called the potential, or the potential energy. So you can call it either one, right? So for such forces where the work done is the same along all paths, the work done is really uh, so we had the integral of the force is minus del v dot ds, and it's of course from point 1 to point 2. Now del v dot ds, this is again very simple vector algebra. This just gives the differential of v. So integrating, we get v2 minus v1, and this just becomes v1 minus v2 with the negative sign outside. So now we have written the work done from 1 to 2 as the difference of the potentials or the potential energies, and above we wrote the work done as the difference in the kinetic energies. There it was T2 minus T1, here it's V1 minus V2. So work done is simultaneously T2 minus T1 and V1 minus V2. And just keep in mind that there were some assumptions that went into these equations, that the mass was constant and the force is conservative. For such systems, we can just take the T1 and V1 on this one side and T2 and V2 on other side. And what do we get? We get that sorry, this is a plus. Yeah, so we get that T plus V is the same at the first point and the second point. So, and these points are arbitrary. You can have it anywhere, right? So what this essentially means is that T plus V is a constant. That the kinetic energy and the potential energy, the sum of those quantities is a constant, and we call this constant E, mechanical energy. So if the force on the particle is conservative, the mechanical energy of the particle is conserved. So this is the law of conservation of energy. Conservation of energy or of mechanical energy. Energy is more generally conserved, but mechanical energy is conserved uh, in these for these in these restrictions. Okay, so this was the mechanics or the Newtonian mechanics of a single particle. Um, let's go further and look at the Newtonian mechanics of a system of particles. So, in general, we won't be just looking at one particle, right? We'll be looking at many particles. So, let's look at the mechanics of a system of particles. Okay, so let's say we have a lot of particles here, and let's denote the particles by J. So let's say that J goes from 1 to all the way up to n. So we have capital N number of particles, and let us, for example, denote one of these particles I. So I can again be any of these particles, but what I is denoting is the particle which we are considering, the particle on which the force is being applied, whose motion we are considering. And J particles are those particles who are applying the force. So this is completely arbitrary, but we're just doing this to make it easy for ourselves to think about these things, right? So we for now we're just looking at the force on ith particle, and I can be 1 to the n or whatever. So what is the force on the ith particle? So the force on the ith particle, well, first of all, there's a force on the ith particle because of this particle, and all the j, all the particles, all the particles labeled j, they apply a force on I, right? So there is a force due to j on I, and this is summed over j, right? But it is important to note that j cannot equal to I, because the ith particle cannot apply force on itself. So if this I is, for example, 2, then there's a force on it because of particle 1, because particle 3, and particle 4, particle n, but not because of itself, not because of particle 2. So it is implied that j does not equal to I here. And we also let's say we also have some force which is external, which is coming from outside of this system of particles. So we are just calling that external force on the ith particle. And by Newton's second law, this of course equals to the time derivative of the momentum of the ith particle. So this is the equation of motion for the ith particle. The net force is the internal force plus the external force, and that equals to its rate of change of momentum with respect to time, right? So what we're actually going to do is we're going to, in our discussion further, assume Newton's third law holds. So assume Newton's third law, and remember what was Newton's third law? Newton's third law essentially stated that the for every action there's an equal and opposite reaction, or for every force there's an equal and opposite force. Equal in what way? In magnitude, and opposite in what way? In direction. So the force applied by I on J is equal to the force applied by J on I. However, it is opposite in direction, so there's a negative sign. So this is something we are assuming. This is not true for all forces, but it suffices for most situations that you will be faced with, and it is a good approximation for most situations. And this is referred to as the weak law of action and reaction. Okay, so we are starting with the weak law because this is all we need. And later on, we will actually need the strong law, and we'll talk about what that is um, to go further. But everything we're doing right now just requires the weak law. So note that we did not really use this in the last section because there was only one particle. But now there are more than one particle, so we have to look at the forces between them, and the Newton's third law, or the weak law of action reaction, just becomes important here. Okay, so what we can do now is, so essentially what we can do now is, um, we can write this equation again, but I'm going to write it slightly differently. So I'm going to write this first. So momentum is, of course, mass mi times velocity. Velocity is dr dt. But um, since there's an another derivative, so this is the second derivative of the position, and I'm just going to write the second derivative of the position here, right? So m double derivative of position is acceleration, and I'm going to write the external force first, and I'm going to write the internal forces next. And what I'm going to do now is I'm going to sum over all the particles. So a sum over I here, a sum over I here. Oh, and there was a sum over j here. So let us just write I and j, sum over I and j, where of course j does not equal to I. As I said that this was implied here, but let me just write this explicitly here. So this is summed over all the particles. And what we're going to do right now is actually define a quantity that will become quite useful in considering systems of particles. And that quantity is called the center of mass. So the center of mass, denoted capital R, is defined as uh, this, the sum of mi ri divided by the sum of mi. So this is essentially a weighted average of the positions weighted by the masses of the particles. And just for convenience, we're going to write the sum of the masses as capital M. So this is just for convenience. Further, what I'm going to do is I'm just going to write that this quantity here, the first quantity on the right hand side, which is the sum over all the particles of the external forces on each particle. I'm just going to write that as Fe, the net external force. So this is just going, just to make things easier for us. And now I'm going to look at the second quantity, and let me just write it here, ij, where just j does not equal to I. of Fji. So the force due to jth particle on the ith particle, this summed over all the particles. What you can sort of notice is that I can sort of write this again, Fji, Fij. So there's a force on j due to I, and there's a force on I due to j, right? So these are force pairs. So for every force due to j on I, there's also a force on I due to j, right? So for each Fji, there's also a force I onto j, and this is present in the sum. But if I want to write them explicitly like this, I can just have this condition here, that j is greater than I. So these are equivalent. The only thing I've done is I've noted that for each Fji there's an Fij in the sum, but I want to represent that explicitly here. And in order to do that, it is not enough for us to say that j does not equal to I. Now I'm saying that j is greater than I. So we are summing over fewer numbers. So for each I, j goes from I plus 1, I plus 2, all the way to n. So there's no double counting anymore. And you can try to write this down for a few numbers and see that this works. But the utility of doing this is that from the weak law of action and reaction, we know that Fij is equal to minus Fji. And Fji minus Fji, this just becomes 0. So sum over all the particles uh, of the internal forces of all the particles, both those that are applying the force and the particles on whom the force is being applied. So the double sum is 0. And this is exactly due to the weak law of action and reaction. Okay, so in our equation of motion, we are denoting this as Fe, we are denoting this just becomes 0. And the left hand side, we can write this in terms of the center of mass, right? So the summation of mi/ri is this, and this just becomes capital M, capital R. Okay, let me just go down. So capital M, capital R, but of course there's a second derivative with respect to time. Capital M is just constant, and on the right hand side we get the external force, and the second quantity is just 0. Okay, now we can further define total linear momentum of the system. So now we're not talking about the linear momentum of a single particle, but of the entire system. So the total linear momentum denoted now capital P instead of small p. Let me just, yeah, is the sum over all the particles of mass times velocity. And velocity, let's just write it as dri dt. And what is this? The sum of mi I, that's just this quantity. So this becomes m capital R. And so m just comes here, and R is in the inside the derivative. So this becomes m dr dt. Okay, so here we have m dr dt, but we have another time derivative. So we can write this equation in terms of the total linear momentum of the system as d capital P dt. This of course equals to the net external force. So this is in some sense, in some way, the equation of motion of the system of particles. And we can further deduce from this that if the net external force on the system of particles is 0, then dp dt is 0, i.e. the total linear momentum of the system is a constant. So this is the conservation of linear momentum. And what is P? P is the linear momentum. It is the linear momentum associated with the center of mass, right? So if the net external force on the system of particles is 0, the center of mass moves in such a way that you can sort of consider it to be a single particle. So you know how a particle uh, would move as it was moving uh, before if there was no external force on it. This is how the center of mass moves if there is no external force on the entire system. The center of mass acts as a particle. It's as if the entire mass of the whole system is concentrated on the center of mass, and that center of mass is moving as a particle. So this was a significant result. Now let us go further and look at rotational motion. Okay, so let me just here. Okay, let us go further and look at rotational motion. I'll begin again with the net force on the ith particle, and just remember what it was. It was a sum over the internal forces Fji and the external force on the particle. Okay, so for the rotational motion, what do we have to look at? We have to look at the moment of these quantities. So what is the force on the ith particle? I know you can remember it is pi dot, right? Because of Newton's second law. And what we can do is we can just take this equation and apply the cross product of vector r I to it to get the moment. So I can do ri, and let me just write this right hand side first. Cross pi dot equals to, and let me again just write the external force first, and then the internal forces, and let me just sum over all the particles as we did before. And there was already a sum here over j, so this is sum over I and sum over j, and of course j does not equal to I. Okay, so now let's look at this quantity first, the internal forces, the moment of the internal forces. So let us just write this here. J does not equal to I, Ri cross Fji, right? So we make a very similar observation to the one that we made before. So we have this quantity here, Ri cross Fji, and I want to write the corresponding quantity here. The corresponding quantity in which way that instead of the force of the jth particle on the I, we also have the force of the ith particle on j, and we have the moment of that force, but of course it has to be with respect to the position of the jth particle, and we of course have this quantity here as well in the sum. But to not do double counting, we put in this constraint. And now what we can do to go further is we note that Fij is just equal to minus Fji, right? So j is greater than I. So I'm just going to take fji outside as common. Here ri just remains as it is, and this is minus fji. Fji goes outside, we get a negative sign. Right. So what is this quantity? So suppose we have some particle here and another particle here. Say this is the origin. So this is the origin, and we have so let's say this is ri, this is j. So this is ri and this is rj, right? So ri minus rj is this vector. It is the vector between the two particles. So this is ri minus rj. So it is a distance vector between the two particles, and we can just denote this as let me just denote this as rij or rji, whichever you prefer. So rgi denotes that it starts at j and ends at I. And what we're going to do now is we're going to assume we're going to make a further assumption. We're going to assume that this force is along the direction of the distance between the the distance vector. So the force of I on j is along this line, and the force of j along on I is along this line as well. And we're going to make this assumption. So this is a stronger assumption than the one we made before. This is called the strong law of action and reaction. So to go further, we are making this assumption, and this is of course isn't true for all forces, but it is true for a lot of them. So as before, we have fji equals to minus fij, right? But further, that the direction, the unit vector of fji is rji. They are in the same direction. So the force lies along the line of the joining particles, the line joining the particles. Okay, so because we make this assumption, because they are in the same direction, the cross product has to be necessarily zero. Right. So let us go back up and even further. Okay, so in the equation for all the particles that we had here, this just becomes zero. What happens here? So r cross f, right? What this essentially is r cross f is the torque. So this is the position of the ith particle and the force on the ith particle due to the external forces. So this is the external torque on the ith particle. So let me write it like this: Ni external. And what is this? This is the moment of the force. This is force, right? Moment of force is again you can it is again torque, but let us just take the time derivative outside, right? Uh, if I take the time derivative outside, what is this? This is r cross p, which is the angular momentum. And let's see if let's see, is this trivial? No, it's not trivial. So let me just show you the steps. Let me just show you the steps. Ri cross pi dot. Let's just write this more explicitly, d by dt. And what is pi? Pi is mi vi, right? So let me just write, uh, uh, add to this vi cross vi. We did this before as well, because this is a 0, and we can write mi here because again this is still 0. And so what this vi here, we can write this as dri dt. So this is the same trick we did before, and the time derivative just comes outside, and this just becomes ri cross mi vi or pi, and r cross p is of course the angular momentum, d li dt. So going back, we have shown that this is the time derivative of the angular momentum of the ith particle, and this is the net torque on the ith particle. Uh, this is the net torque due to the external forces. So of course this is sum over I. So let's just go down again and write. So we have the sum over I of dli dt, and this equals the sum over I of the net torque on the torque on the ith particle due to external sources. Right. So the summation can go inside the time derivative, and we get the sum over all the uh, particles' angular momenta. And let us define that as capital L. So this is the total angular momentum. So the total angular momentum of the system. So we're defining the total angular momentum of the system like this. And further, let us just write this as the net torque as this. So no sum. We have summed over all the particles, and we have obtained, and we're just calling this the external torque, net external torque on the system of particles. And this is finally the equation of motion for rotational motion for a system of particles. And going further, we can deduce that if the net external torque on the system of particles is 0, then the total angular momentum is a constant vector. And since the total of and what this essentially gives us is that if the net torque, external torque on the system is 0, then the total angular momentum defined in this way is a constant vector. This is the conservation of angular momentum. Okay, so what we have done here is we have obtained the equation of motion for rotational motion for the system of particles, but we have not yet written the angular momentum in terms of the center of mass, which we did for the linear momentum. So let us now do that. Right. So let us first consider particle I. So the radius vector of this particle is Ri, and let us now write the center of mass like this. So this is the center of mass, this is the position of the particle I, and let us now consider a different coordinate system, a coordinate system where a coordinate system in which the center of mass is the origin. So in that coordinate system, the position of the particle I, the position vector would be like this, and let's call that uh, Ri prime. So this is a prime coordinate system, and this is the original we only had. This is origin O, this is origin O prime in the new coordinate system. And right now, So what we have defined Ri prime as radius vector of I in uh, or from the center of mass. So the total angular momentum, uh, actually, before we get into onto the total angular momentum, let me just write uh, what Ri prime and related quantities explicitly are. So Ri is just capital R plus Ri prime. Okay, so just we're just writing Ri in terms of the position vector in the new frame of reference. So Ri is capital R plus Ri prime, right? So capital R plus Ri prime. And we can take the time derivative to get the velocities. And let us just define small v as the time derivative of the center of mass. So this is the velocity of the center of mass. And vi prime is the velocity of the ith particle in the reference frame in which the origin is the center of mass itself. Now, in this new reference frame, I want to write the angular momentum. The total angular momentum is the sum over the individual angular momenta r cross p, and we can write r in this way and p as mass times this. So let us do that. So ri is capital R plus ri prime cross p is mass times the velocity in this new reference frame. Okay, so there's no I here because this is for the center of mass. Okay, now we can do this multiplication and we'll get four terms, right? So let me just write each one individually. So sum over I of R cross MIV. So this is the first term. So for the second term, let's do the second term for in each bracket. So Ri prime cross MIVI prime. Okay, so for the third one, let's do this one. We have Ri prime cross MIV, and for the fourth one we have R and VI prime. So this summation over I capital R cross MIVI prime. Okay, so uh, let's look at each one of them a bit more carefully. Uh, so here there is only summation over M. So let us just write that separately and we get R cross V plus here we have some more all of the terms, but we can write this as mass times V as the momentum. So this becomes the momentum in the primed coordinate system, in the coordinate system with the center of mass in the origin. Here, what we can do is we can we note that there is no summation on V, so we write the summed quantity separately cross V. Okay, and here there is no sum over R, so we again write the summed quantity separately. And this is d by dt of r, so I'm just going to write this as d by dt summation I m I r I prime. Okay, so again, each one separately, this becomes the total mass, so r cross total mass v plus, and I'm just going to write this. Okay, this was a prime here which I missed. Yeah, I'm just going to write it as it is. This is in the form that we desire. Now on to these. So what do we have here? What do we have here? So note that the center of mass was the sum over mi ri divided by the sum over mi, right? What if we write the center of mass in the primed frame? What would we have then? We would have ri prime instead. The masses of course don't change, they are constants. However, what does this actually signify? This actually signifies the distance vector from the origin in the prime frame to the center of mass. But remember, the origin in the prime frame is the center of mass itself. So this is really the radius vector from the center of mass to the center of mass, and which is of course 0. Therefore, mi ri prime, the sum of this quantity has to be 0. So this quantity has to be 0. And it's a similar thing over here. Mi ri prime, the sum of that is 0. And finally, what we had on this side was the total angular momentum. We finally have it as follows. So what this first quantity denotes is the angular momentum concentrated about the center of mass. So these are all center of mass quantities. M is the total mass of the system. This is the radius vector of this, this is the center of mass in the uh, original reference frame, and this is the velocity of the center of mass in the original reference frame. But further, we have everything in the center of mass reference frame, and these are the individual angular momenta of each particle in the center of mass reference frame. So this is the this is the angular momentum of motion about the center of mass. This is the angular momentum of the concentrated on the center of mass. This is the angular momentum of motion about the center of mass. So we have derived the quantity that we desired, the angular momentum in terms of the center of mass quantities. Now finally we can go on to work and energy. So remember, work done from now work done has to be thought of differently, because 1 and 2 are not simply positions of some particles, but they are positions of many particles. So let's say the particle I starts here and goes to here, j starts here and goes to here. So there's an initial configuration which is denoted 1, and a final configuration which is denoted 2. So there are many particles. They are all n particles which are going through some change. Now the work done has to be the sum over all the particles, and the work done by each one of the particles. So 1 to 2 fi dot dsi. Right. And let us just look at the look at this quantity in terms of velocities, in terms of motion. So what we can do is we can write the force in terms of using the equation of motion, Newton's second law, as p dot. P dot is just mi vi dot, and we can write this as dsi dt, which becomes vi. Oh, I wrote prime here instead of dot. So this is a vi, and this is dt. Okay. So I'm not going to redo the simple mathematics that we did before. This becomes half m vi squared. So differential here. So these are the same steps that we did before, and this becomes T2 minus T1, where T is now the sum over the individual kinetic energies. So this is the kinetic energy of the entire system. Okay, so let us, before proceeding further, write the kinetic energy in terms of center of mass quantities. Let us do what we just did before for the angular momentum. Let me just take half outside. We have mi here. Vi square is vi dot vi, and vi was v plus vi prime, center of mass, plus the position of the particle in the center of mass frame. And so the first one just becomes v square. The second one just becomes mi, and this one, let's just do vi prime, vi prime square. So the third and the fourth, the cross terms are the same. So they add up to get rid of the half, and we get summation mi v dot vi prime, right? Now, you can sort of write this as v dot summation I mi vi prime, and this is of course the from the center of mass being 0 in its own reference frame. This just becomes 0, so this term just goes away, and we get half sum over the masses is capital M v square plus half mi vi prime square. So what is this? What does this mean? So this is the kinetic energy if all the mass was concentrated at the center of mass, and this is the kinetic energy of the motion about the center of mass. So again, similar term to what we got before from the angular momentum. But so we have two results here. This is the form of the kinetic energy in terms of the center of mass quantities, and we know that we have found that the work done is still the difference between the difference in the kinetic energies, where the kinetic energy is now the total kinetic energy of the entire system. Let us now again look at work done, again making the same assumption that all the forces are conservative. So let us make those assumptions individually. But first, let me just write the work done in a form that we can make that assumption. So work done is the summation from 1 to 2 integral f fi dot dsi, and let me just decompose the force into internal and external forces. So we have the external force on the ith particle, and we have the internal forces, force due to j on I dsi. So here we have a sum of over I and j, where j does not equal to I. Everything as we did before. Okay, so now we are assuming that all the forces are conservative. As far as the external force is concerned, what that means is, let us just consider this first. What that means for the external force is that this becomes minus del I vi. Of course, we have to specify what are the coordinates of the nabla operator. So those are I, of course, dsi. As before, this becomes dvi, and we get minus outside summation over I of vi 1 2. Okay, so this is the first one. Now let us consider the second term. We are again assuming that the forces are conservative. Now, as for the potential uh, associated with this internal force Vij, this has to be a function of the Ri minus Rj and the magnitude of that. And this by the strong law of action and reaction. That since the force is on in the line of along the line along the unit along the line of the vector between the two particles, potential has to be only a function of this quantity. So this is this just comes from the strong law of action and reaction. So now let us just consider the second term, summation ij, j does not equal to I, integral 1 to 2 f ji dot dsi. Okay, so give the summation and with the integral. So this becomes minus del I v ij, and note why we have I over here, because this is for the ith particle, right? So dsi, and this so what we do now is we do the same thing we have been doing when we are considering the internal forces. We're going to write the terms more explicitly. So for each Vij, Vij, there has to be a Vji as well in the sum, right? But of course, the indices over the other quantities change as well, right? Because there's a sum over I and j. Now j has to be greater than I. We make the same, the same thing we did before. We write these explicitly. Now Vij and Vji are the same from the strong law of action and reaction, because they're only dependent on the magnitude and not on the direction. So writing this as follows, Vij and Vji are the same, and further del I and del j are same except for a negative sign, right? Because you can make a coordinate transformation from I to j, but you'll only get a negative sign there, and everything else would be the same. So you can take the del I Vij outside, and you have dot product dsi. Since we change this del j to del I, we get minus dsj. So we get a negative sign over here because of this. Now this just becomes, let us just write this as dsij or drij, whatever you want to write, and this entire quantity will become dvij. So everything is similar to what we have done before. Now this becomes minus with a minus sign, summation I j greater than I. We integrate over, uh, we integrate over the whole thing. Uh, we get Vij 1 2. But the summation over here is different from the summation here, right? It's slightly different, and we have this, we have this constraint that j has to be greater than I. I don't really want this constraint. This constraint is, I want to be just able to look at the equation and do the sum immediately. So what I'm going to do is I'm going to get rid of this constraint. I want to have just this constraint, the weaker one, that the j does not equal to I, which is implied anyways. And then So what we are doing is we are not doing double counting, but because we are doing double counting, we can just put a half over here, Bij, and there you go. So this is the second term from the potential. This was the first term, the second term, and the first term. Now we can write the work done uh, in terms of the potentials. We have a negative sign, and we had the summation of Vi, where this was due to external forces, and we have the half internal force quantity here, Vij, and this goes from 1 to 2. And what we're actually going to do is we're going to define this as the total potential V. So this becomes the total potential, and this is of course V1 minus V2 because of the negative sign here. So comparing this with as before, with the quantity before, we have T2 minus T1 equals to V1 minus V2, and as we did before, T1 plus V1 is equal to T2 plus V2, and this is of course a constant which we call E, the energy. So if the external and the internal forces are conservative, and if you assume the strong law of action and reaction, then the total energy is conserved. This is the law of conservation of energy. In this video, what we essentially did was we looked at Newtonian mechanics of a single particle and of a system of particles. And we have derived the conservation laws, and we've looked at the center of mass and quantities, different quantities in terms of the center of mass. And we're done.